to get started on topic 1.11. So it is equivalent representations of polynomial and rational functions. So in the 1.4 to 1.6, we talked about polynomial functions. In 1.7 to 1.10, we talked about rational functions. So we're going to start to kind of take a look and zero in on all the details about these types of functions that we need to know. So the first example we're going to take a look at is our rational function. So it says recall that h of x equal f over g of x. If g of c equals 0, then h of x has a vertical asymptote or hole at x equals c. Okay, so what's going to happen here is this. We're going to start to fill in all the different blanks here, and we're going to take a quick sketch of our graph as well. So first thing we're going to do is we're going to need to factor. So when we look at our factor, we have x minus 4 over times x plus 3, and then we have x plus 5, and x minus 4. Okay, as we take a look at the degrees, the factor form is right there. If we take a look at degrees, the numerator is a degree of 2, denominator is a degree of 3, so that means that this is bigger on the bottom. So because it's bigger on the bottom, this would be Bobo as well. So find any zeros of the function for k of x. Find any values of x where there's a hole. So the first thing I notice is there is going to be a hole. Okay, so the values of x where there's a hole, that would be x equals 4. Okay, find any zeros of the function. So the zeros of my function would be at x equals negative 3. So the 0 would be the x-intercept. Okay, if I wanted to find the location of the hole, I got x plus 3 over x times x plus 5 remaining. So if I substitute the 4 in there, so the 4 plus 3 is where I get 7. I have 4 times 4 plus 5, which is 9. So that would be 7 over 36. So 7 over 36. That would be the location if I really needed it. Okay, find any vertical asymptotes. I have 2 of them. One is at x equals 0, and the other is at x equals negative 5. And those come from my remaining factors in the denominator. The zeros comes from the numerator right there in green. Okay, and then whole comes from the x minus 4s that ended up canceling there. Okay, so color coded so you can kind of see it a little easier. Because this is bigger on the bottom, I do have a horizontal asymptote at y equals 0. Okay, domain, everything except my asymptotes and hole. So what that means here is if I think about a number line, I do not want to have 0, I do not want to have negative 5, and I do not want to have 4. That's where my function has zeros in the denominator. So it's everything except that. So that means negative infinity to negative 5, negative 5 to 0, 0 to 4, and then 4 to infinity. All real numbers except those 3 values there. Okay, use the sign chart to help sketch the graph. So I have vertical asymptotes at x equals 0 and x equals 5. 1, 2, 3, 4, 5. I have a horizontal at y equals 0. I have a hole at 4, 7 over 36. So 18 over 36 is a half, so somewhere there. Okay. Y-intercept, if I let x equals 0, so y-intercept, if x equals 0, I get negative 12 over 0, which is undefined. That means that I do not have a y-intercept. It also makes sense because on the y-axis, I have a vertical asymptote. Okay, so now what we're going to do, we're going to go with a sign chart to help us out here. I have a 0 at negative 3 as well. So I have 3 important numbers. I have negative 3, I have 0, and I have 5 to worry about. So let's see here. Oh, I have my vertical asymptote in the wrong location. So let's fix that. I noticed that it said x equals negative 5, not positive 5. 1, 2, 3, 4, 5. So let's try that again and place this here. And that will change my sign chart ever so slightly. So as I fix my sign chart, I have -5, which is a vertical asymptote. I have -3, which is a zero of my function. And then I have 0, which is also a vertical asymptote. Okay, so I'm going to use the factored form. I'm going to go to the right of 0. So when I go to the right of 0, I'm going to use, well, actually, I see where the hole is. The hole is already above it, so I can use that. But I'll just use 1. So if I use 1, 1 minus 4, 1 plus 3, 1 is positive, 1 plus 5, 1 minus 4. So I see 2 negatives there. My answer is positive, which is what I was expecting because the hole is above the x-axis. Okay, -1, so -1 minus 4, -1 plus 3, -1, -1 plus 5, -1 minus 4. 3 negatives, I am below. -4, so -4 minus 4, -4 plus 3, -4, -4 plus 5, -4 minus 4. I got 4 negatives, so I am above the x-axis there. And then -6, so -6 minus 4, -6 plus 3, -6, -6 plus 5, -6 minus 4. 5 negatives means that this is negative. Okay, when I look at my zones here, okay, vertical asymptote could be above or below, and behaviors over here, asymptote, asymptote, and behavior there. Okay, so to the left of -5, I am supposed to be below the x-axis, so to the left of it, I'll use a different color. So I'm looking at something where it curves to both of those there. Okay, between 3 and 5, -3 and -5, I'm above, so -3 to -5, I am like that. I'm going to cross over into the negative, so I'm going to cross over to the negative and head towards that asymptote. Okay, and then to the right of 0, I am positive, so to the right of 0, I'm going to head towards the hole and then towards the horizontal asymptote like that. And that would be my graph. Okay, write the end behaviors in limit notation. So end behaviors, make sure you know that it's as x approaches -infinity of k of x, and the limit as x approaches +infinity of k of x. And because I might have my horizontal asymptote of 0, on the left end, I'm headed towards 0. On the right end, I'm headed towards 0 also. Okay, left and right limit statements as x approaches 0 and 4. So let's see, limit as x approaches 0 from the left. So to the left of my vertical asymptote, my graph is headed down to -infinity. The limit as x approaches 0 from the right of k of x. So to the right of my vertical asymptote, my red line, my graph is headed up, so that would be +infinity. Limit as x approaches 4 from the left of k of x, it's headed towards the hole. So the hole would be located at 7/36. That's what I calculated. And the limit as x approaches 4 from the right of k of x is going to be the same thing. It would be 7/36. Okay, so that's our review of our rational function number 1. Okay, let's pause here and let's have you guys try example number 2. Try to create your rational functions based on the zeros, based on the vertical and horizontal asymptotes, and based on the holes. Pause here. Okay, let's see how we did on example number 2. So for this first one, just a couple of things that I noticed. The first thing that I noticed is I have a vertical asymptote at x equals 2. I noticed that I have a horizontal asymptote at y equals -1. I know that I have a hole at x equals 4. And then the last thing I notice is that I have a 0 at x equals 3. Okay, so that's going to tell me a lot of things about my function. So when I'm going to rewrite my function, I got f of x equals. So with a vertical asymptote at x equals 2, that tells me my denominator is going to have x minus 2. So if I have a 0 at 2, x minus 2 is linear factor. Okay, because I have a hole at x equals 4, that means that I had an x minus 4 that ended up canceling out. So the x minus 4 will be accounted for there. Because I have a 0 at x equals 3, I notice that I know x minus 3 should be in the numerator. Okay, and then the last thing, because I have a horizontal asymptote at y equals 1, that means that the bottom degree is equal to the top degree. We got a Betsy. So I notice that I have x squareds on the top and the bottom. And so that my coefficients should be negative 1 over 1, or so on top or bottom. So what that means is that I need to have a negative sign on the top or the bottom to account for the negative 1. Okay, what I will double check here is the end behavior. So if I just make a sign chart, okay, all I'm looking at are the last values on my x-axis to the left and the right. So the ones that I'm going to take into consideration that I'm going to look at is I'm going to look at my vertical asymptote at 2. That will show up on my number line. And then I am going to take a look at my x-intercept, which is 3, because I only have one x-intercept and one 0. I'm sorry, one x-intercept and one vertical asymptote. So this point is here. Okay, and then so what I'm looking at is my sign chart. So to the right of 3, I see that my graph is below the x-axis. So I know that it's negative to the right of 3. And as I look at my sign chart to the left of 2, I notice that my graph is below. So that means that to the left of 2, I also have a negative. So because my end behaviors are both negative and negative, there's two things it tells me. It tells me that my lead coefficient should be negative and that my degree should be even. Well, when I look at my function, I see that I have an even degree, x squared over x squared, and I see that I have a negative lead coefficient, which is negative 1. So therefore, I am good and accounted for. Everything's good. Okay? For the second one, I am looking at g of x. So when I am looking at g of x, there's a few things that I want to account for. So I have vertical asymptotes. I have 2 of them. I have it at x equals 0 over here that you can't see the greatest. And then you also have one at x equals 3. Okay, I also have a horizontal asymptote at y equals 0. I see that I have a hole at x equals 2. And then I have one x-intercept. I have a 0 at x equals 1. So there's a lot going on here. Okay, so I'm going to rebuild this function. So I have g of x. So I have 2 asymptotes, vertical asymptotes. When x is 0, that means I have x as a factor, and I have x minus 3. So that accounts for my 2 vertical asymptotes. Okay, horizontal asymptote, I'll get to in a moment. I'll account for the whole. So if it's at x equals 2, that means that I have a x minus 2 on the top and the bottom. Because I have a 0 at x equals 1, that means that I have x minus 1 in my numerator. Okay, horizontal asymptote at y equals 0. That means that we worked with Bobo, bigger on bottom. So what I notice at the moment is that I have x squared on the top and x cubed on the bottom. So that's accounted for as well. So we're doing good there. The last thing I need to account for is the end behavior. So one more time, I'm going to take a look at my end behavior. So on my farthest left, I am looking at, what color did I use? I'll just follow it, blue and then green. So on the farthest left, I have my vertical asymptote at 0. So I'm going to use 0. And then on my farthest right, I have my vertical asymptote at 3. So that means that this number is going to be 3. So when I look to the right of 3, what I notice is my y values are below. And when I look to the left of 0, my y values are above. So what this tells me is this is a falling end behavior. So that means that my lead coefficient should be negative and that I have an odd degree. So when I look at my function g of x, right now my lead coefficient is not negative. So what that means is I need to throw a negative sign in there to account for it. And that's how I make sure that my end behavior ends the way that it's supposed to. Okay, so that's why we want to take a look at the end behavior, just in case we need to get that negative sign in. Okay, so let's turn the page. So it says, recall, given a rational function, if the degree of the numerator is 1 degree greater than the degree of the denominator, we will have a slant asymptote. So the function k of x, as they show here, okay, it is 1 degree larger in the numerator as graphed above. It has a whole at x equals 2 because the x minus 2 will cancel out. It has the vertical asymptote at x equals -1. It does not have a horizontal asymptote, but it does have a slant by doing polynomial long division there. Okay, since the degree of the numerator is 1 greater, we know k of x would have a slant asymptote. So it's just a real quick review of long division that we've done before here. Okay, so when we do long division, so just a real quick refresher on how we used to do this one. So we would put the 21 over here, and we put the 676. And then, so we would say, how many times does 21 go into 67? So that would be 3. We get a 63. We would subtract to get 46. There's a 2 there, so 2 times 21 is 42, so it's a 4. So we have a remainder of 4. So my quotient would be 32. My remainder would be 4, so it would be 32, and then plus the 4 over 21. Or what we would consider 32 and 4 over 21, right? So that's one way. So when we do the 2x plus 1, 6x squared plus 7x plus 6. So we look at the first terms. So 2x times 3x is how you get 6x squared. So that's 6x squared plus 3x. I'm going to sign change because I'm subtracting. So 7x minus 3x is 4x. So 2x times 2 is how I get 4x, positive 2. So this gives me 4x plus 2. I'm going to sign change. I'm going to sign change. I'm left with -4. Okay? So, I'm sorry, not -4, positive 4. So my quotient is 3x plus 2. My remainder is 4. So this would be 3x plus 2 plus my remainder over divisor, like that. Okay, and so that would be my answer there. Okay, so what I want you guys to try to do here is we're going to pause. We're going to just quickly go through examples 3, 4, and 5, and then we will see how we did. So pause here, try them out, and then start up the video again. Okay, let's see how we did on these examples. So the first thing that we're going to want to try to do here is we're going to look at the degree. So vertical, horizontal, slant asymptotes. So this is bigger on top. So this is bottoms. Because it's 1 degree larger, there will be no horizontal asymptote, but I will have to do polynomial long division to find my slant asymptote. 6x squared plus x plus 5. Okay? So when I take a look at this, 2x times 3x, so I have 6x squared plus 3x. I will sign change, subtract, subtract. So 1 minus 3 is -2x plus 5. Okay, what times x gives me -2x? That would be -1. So -1 times 2x is -2x. And then this is -1. Sign change, this becomes a plus. This becomes a plus, so I'm left with a remainder of 6. Okay, so in this case, slant asymptotes is going to be y equals 3x minus 1. Okay, vertical asymptote, my 0 of my denominator, so x equals -1/2, because when I said 2x plus 1 equal to 0, that's where the -1/2 comes from. Okay. Example number 4. Which of the following is correct? So this is 2x times x times x. That means that I have a 2x cubed. So I'm looking at a buttons here. So horizontal asymptote, there are none. Okay, there is a slant asymptote. If I factor the denominator, that would be x minus 1 quantity squared. Okay, so when the x minus 1 on the top takes away the x minus 1, one of them from the bottom, it's still there on the bottom. So therefore, there is no hole created. My answer would be D. Okay, and the one vertical asymptote would be x equals 1, the remaining part there. Okay, so that would be example number 4. Example number 5. So what we want to do here is we want to sketch a picture. So as x approaches infinity, you should be going down towards negative infinity. As x approaches negative infinity, you should be going up over here. As you approach negative 1 from the left, you should be going down. As you approach negative 1 from the right, you should also be going down. So what I'm guessing here is my graph should be kind of going like that. And then something like that. Okay, and so that would match my description of here. Okay, so turn the page. We're going to get started on Pascal's triangle. So for Pascal's triangle, we're going to be talking about expanding binomials. So if we take a look at our first example, if I wanted to expand x plus 3 quantity squared, that's just going to be x squared plus 6x plus 9. If I wanted to do x plus 3 quantity cubed, what I'm going to do is I'm going to do a x plus 3 times the x squared plus 6x plus 9 that we just did. You could do a distributive property where you distribute the x and then the 3, or what you could also do is do something like a box multiplication, and that kind of keeps you a little more organized as well. Your choice on which you prefer. So x cubed plus 6x squared plus 9x plus 3x squared plus 18x plus 27. So what happens here is your diagonals are your like terms that you can combine with each other. So therefore, we'll be looking at x cubed plus 9x squared plus 27x plus 27. Okay, but what if we wanted to do x plus 3 to the 7th power, quantity to the 7th power? So this is going to be tedious, time consuming, so there is a great mathematical property to help us out. So it's called the binomial theorem. So a couple of things to point out in binomial theorem. The first term in your binomial is going to appear every time there until the very end. Your second term in your binomial is your b value. So notice it's not in the first, but it appears until the very end. And then the exponent, the nth power. So notice that for your a value, it starts with a and then it decreases by 1 and decreases by 1 until it's gone. And then for b, it starts at the back side and it decreases by 1 until it's gone in the front. So a couple things. When you're expanding a binomial expression, a begins with the degree n, b term begins with the degree 0. As we expand, the degree of a decreases by 1, the b increases by 1. We can use Pascal's triangle to find the value of the coefficients. So these last things that we need to account for are these coefficient numbers here. These coefficient numbers come from Pascal's triangle. So Pascal's triangle starts with a 1 on outside, and then what happens here is you just start to add in order to get these numbers here. So 3 plus 1, 1 plus 4, 4 plus 6, 6 plus 4, 4 plus 1. Okay, and that's how you get the next numbers down. And so what's going to happen here is these numbers in each of these rows are going to correspond with the coefficients that go into your expansion. So it says the first number in each row is the 0th element. So this is 0, this is the first element, this is the second, this is the third, fourth, fifth, and then sixth. Okay, so that's kind of what they're referring to there. So what happens here is this. In Pascal's triangle above, the 5th row is circled. Okay, so that's row number 5 with the degree of 5. The first number 10 has also been circled. The circled 10 is the second element, and that's because this is the 0, this is the first, this is the second element in the row. So what happens here is 5th row, second element, that's how you get 10. That's also what we call a combination, and that's where we do the 5C2 that you learned in geometry. So that's 5 factorial over 2 factorial, 3 factorial. So 5 times 4 times 3 factorial, 3 factorial times 2 times 1. So the 3's are going to cancel, and you're just left with 20 times 2, which is 3. 20 divided by 2, which is 10. Okay, but again, they don't need you to know that how to do combination. That's just where it came from. So let's just talk about how to use this. Okay, so we're going to use Pascal's triangle to expand x plus 2 to the fifth power. So a couple of things we want to know. First of all, your first term in your binomial is x. The second term in your binomial is 2, the x and the 2. Because it's a plus sign, every single term is going to be addition. Okay, it's to the fifth power. So the first thing I'm going to put down is I'm going to put down my coefficients. So because it's to the fifth power, you're always going to have one more term. So 1, 5, 10, 10, 5, 1. That's where the rows came from. Okay, it goes x to the fifth, x to the fourth, x to the third, x squared, x, and it goes 2 to the fifth, 2 to the fourth, 2 to the third, 2 to the second, 2 to the first. Okay, so all I did was I went in increasing, decreasing order. I'm going to separate them with plus signs. Like that. Okay, and so now it's just a matter of simplifying. So I have 1x to the fifth, so that's going to just tell me x to the fifth power. That's 5x to the fourth times 2, so 5 times 2 is 10x to the fourth power. 10 times 2 squared is 40, so 40x cubed. 10 times 2 to the third power, so that's 10 times 8, so that would be 80x squared. I have 5 times 2 to the fourth power, so 5 times 16 is also how I get 80x. And then 2 to the fifth power is 32. So this would be my expansion without having to multiply it by itself 5 times. Okay, so that's how I would use Pascal's triangle. Using Pascal's triangle to expand 2x to the fourth power. So I know my a is 2x, I know my b is 1. Because it's minus, what's going to happen is it's going to alternate. Minus plus, minus plus. Okay, because the exponent is 4, there's going to be 5 terms in the end. So I'm going to start off with row 4. So that tells me 1, 4, 6, 4, 1. That's how I know there's going to be 5 terms. Okay, I'm going to have 2x to the fourth power, 2x to the third power, 2x squared, 2x to the first, and then 2x to the 0 is gone. Now I'm going to work backwards the other way. 1 to the fourth power, 1 to the third power, 1 squared, 1 to the first power, and then nothing there. And now again, signs. So signs, it's going to alternate. Minus, plus, minus, plus. Okay, so it's just alternating every single time starting with the minus. So 2x to the fourth power, the quantity of 2x. So 2x times 2x times 2x times 2x, that's 16x to the fourth power, minus 4 times 8, 32x cubed, plus 6 times 4, that's 24x squared, minus 4 times 2, 8x, plus 1. And that would be my answer. Okay, example 8, what is the coefficient? So we're looking for a number containing x to the fourth. So what that means is, if you keep in mind, your a is x, so it would go x to the 6, x to the 5th, x to the 4th. I want my third element in. So as I go to my third element in, okay, third number in, so that would be my 1, my 6, and my 15 when I'm looking at this row. So I'm looking at the 15 there. So 15, that would mean x to the fourth, and that would mean 5. Now what you'll notice here is every single time when you add your exponents together, it always adds up to n. So because I'm using 4, that means that this is going to be 2, because 4 plus 2 is how I get 6. So all I have here is 15 times 25. So that means that this is 375x to the fourth power. That's the term. So all I want is the coefficient. So the coefficient is going to be 375. Okay, and then the last one, I want x cubed. What is the coefficient containing x cubed? So I know that there's going to be an x cubed, and it's going to be 3 to the fifth power. Okay, because I don't know whether it's the plus minus, I'm just going to treat it as negative 3 at the moment. So that way it's accounted for. Because it's 8, if I look at Pascal's triangle, I'm missing it. So I got to do this. So 1, 8, 28. So again, I'm just adding these things together, right? 56, 70, 56, 28, 8, and 1. Okay, so I need to get to x cubed. So that means that this is 8th power, 7th power, 6th power, 5th power, 4th power, 3rd power. So 3rd power means that I'm going to be using the coefficient of 56. So that means this is 56. I don't know why I put a 5 there. That should be x to the 3rd power because that's what we were working with. And then negative 3 to the 5th power. So 56 times negative 243 times x cubed. So this would be negative 13,608 x cubed, but I only want the coefficient, so negative 13,608. Okay, so that's how we use Pascal's triangle, and we are done.